A neural network has a fixed number of neurons. And yet, when we look inside large models, they seem to track an astonishing number of distinct concepts, far more than they have neurons. So here's the puzzle at the heart of this paper from Anthropic. How can a network represent more features than it has dimensions? And could the answer also explain why individual neurons are so frustratingly hard to interpret? To get at this, the authors do something clever. Instead of wrestling with a giant model, they build a tiny one, a toy model, simple enough to understand completely, but rich enough to show the real phenomenon. The phenomenon is called superposition. Before we can talk about packing features, we need to say what a feature is. Loosely, a feature is some property of the input that the network finds useful to represent. Is this an image of a cat? Is this text in French? Is this part of a curve? The key working assumption is the linear representation hypothesis. It says features correspond to directions in the network's activation space. To represent several features at once, the network simply adds up their direction vectors, each scaled by how strongly that feature is present. Representations are built by superimposing directions. That word, superimposing, is about to become important. Now suppose every feature got its very own neuron, one clean direction each. Then a layer with, say, 500 neurons could only ever track 500 features. That's incredibly limiting. Superposition is the alternative. The network packs many more features than it has dimensions into the same small space, storing them as overlapping, non-perpendicular directions. The analogy the authors use is radio. Many stations share one slice of the spectrum, and as long as they don't all broadcast loudly at the same instant, you can still pull out the one you want. A neural network, it turns out, can do the same trick with features. Superposition has a telltale side effect, and it's something interpretability researchers had been complaining about for years. If features share directions, then any single neuron is a blend of several of them. So when you look at one neuron and ask, what does this fire for, the honest answer is several unrelated things at once. Cat faces in the fronts of cars and maybe be the texture of fur. That's a polysemantic neuron. The crucial reframing here is cause and effect. Superposition is the underlying cause. Polysemanticity, the messy multi-concept neuron, is just the symptom we happen to see from the outside. So how do you study superposition in a controlled way? You force it. The toy model takes a set of n features and squeezes them through a bottleneck of only m dimensions, where m is much smaller than n, and then tries to reconstruct the original m features on the other side. Concretely, it projects the input down with a weightrix w, giving a small hidden vector h. Then it projects back up using the transpose of that same matrix, adds a bias, and applies a real u. It is, in essence, a linear autoencoder with a single nonlinearity. Because the bottleneck is too small to give every feature its own dimension, the model is forced to make hard choices about what to keep and how to pack it. The choices the model makes depend entirely on the data, and the data has two important knobs. First, sparsity. Each feature is switched off most of the time, becoming active only with some small probability. Real-world features are like this. The concept Golden Gate Bridge is absent from almost everything you read. Second, importance. Some features matter more to the reconstruction loss than others, so the model has an incentive to protect the important ones. We train the model to rebuild its input as accurately as possible, weighting each feature's error by its importance. Then we simply watch what internal structure it chooses as we turn those two knobs. Everything in this paper flows from one tension. On one hand, the model could give a feature its own dedicated dimension. That's clean, perfectly readable, zero interference, but it burns a whole dimension on a single feature, and the bottleneck only has a few. On the other hand, the model could let features share dimensions. That fits far more of them in, but the moment two features that share a direction are active together, they interfere, and the reconstruction takes a hit. Dedicate and stay clean, or share and risk collisions. Which strategy wins? As we'll see, it comes down almost entirely to how sparse the features are. And here is the central result of the whole paper in one picture. Each panel shows the learned feature directions as sparsity increases from left to right. On the left, at zero sparsity, features are dense, active all the time. The model plays it safe. It gives its two most important features their own clean, orthogonal dimensions, and it simply throws the rest away, mapping them to 0. In the middle, at 80% sparsity, it gets bolder, packing 4 features in as antipodal pairs, opposite directions that share an axis. On the right, at 90% sparsity, all 5 features are squeezed in, arranged as a pentagon, accepting a little interference, because collisions are now so rare. Sparsity is the dial that turns superposition on. To see this happening inside the model, we need to read its weight matrix W, and there are 3 equivalent ways to look at it. As a matrix, where rows are features and columns are neurons. As a stack plot, where we color each feature and stack its weights per neuron. Or as a graph of connections, the way we usually draw neural nets. These views give us a precise, visual definition of the thing we care about. A neuron whose column contains just one color is monosemantic. It carries one feature. A neuron whose column stacks several colors is polysemantic. It carries several features in superposition. Now we can literally see the difference. Another revealing view is the matrix W transpose W, which tells us how features end up related in the hidden space. When the model uses dedicated dimensions, this matrix is essentially the identity, a clean diagonal. Each feature maps to itself and ignores the others, the picture on the left. But when the model uses superposition, off-diagonal entries light up, the picture on the right. Those are exactly the interference terms, features bleeding into one another, because they share directions. So a single matrix captures the whole strategy. A clean diagonal means no superposition. A busy, off-diagonal pattern means the model has chosen to pack features together. Let's make the intuition airtight, because it's the linchpin. Superposition only costs you when 2 features that share a direction are active at the same time. That's when they interfere. But if features are sparse, each one is active only rarely, so the chance that 2 specific ones collide in the same example is rare squared, vanishingly small. The model does the implicit math. The benefit, fitting in another useful feature, is paid every example, while the cost, an occasional collision, is paid almost never. So the sparser the features, the more lopsided that bargain becomes, and the more aggressively the network superimposes. If you sweep across both knobs, sparsity and relative importance, and ask what the model does with a single extra feature, you get this phase diagram, and it's remarkably crisp. There are 3 regions. In gray, the feature is so unimportant or so dense that the model doesn't represent it at all, it just drops it. In blue, the feature is important enough to earn its own dedicated dimension, and in red, the feature is stored in superposition, sharing space as an antipodal pair. The bottom panel shows that a clean theoretical model predicts these same boundaries. Superposition isn't a fluke of training, it's the optimal solution in a well-defined region. Reading that diagram gives a simple story for who gets superposed. Importance pulls a feature toward its own private dimension. The model spends its scarce clean dimensions on the things that matter most. Sparsity pushes everything toward sharing, because when activations are rare, sharing is nearly free. Turn up the sparsity and the red superposition region grows, swallowing more and more features, even the moderately important ones. And the striking thing is that this same phase structure keeps reappearing as you scale the model up. The rules that govern a 2-feature toy seem to govern much larger systems too. Now for the part that's genuinely beautiful. When the model decides to pack several features into a shared space, it doesn't throw them in randomly. It spreads their direction vectors as far apart from each other as geometry allows, because the further apart they are, the less they interfere. The result is that features arrange themselves into the vertices of regular shapes. 2 features become an antipodal pair pointing in opposite directions. 3 become an equilateral triangle. 4 become a tetrahedron in 3 dimensions. The network rediscovers classical geometry, the most symmetric packings known, purely from minimizing reconstruction error. The authors make this precise with a quantity they call feature dimensionality, roughly, how much of a dimension each feature gets to claim for itself, and when you plot it against sparsity, the features don't slide around smoothly. They lock onto specific, tidy fractions, marked by these colored bands. A dedicated dimension is 1. An antipodal pair is 1/2, 2 features sharing 1 dimension. A triangle is 2/3. A tetrahedron is 3/4. There's a pentagon, a square, antiprism, and more exotic shapes too. The top row shows the actual learned geometries that produce each fraction. The network parks at these special configurations, like a physical system settling into stable states. Why these particular fractions and not a smooth continuum? Because they correspond to uniform superposition, configurations where every feature is treated symmetrically and interference is spread out as evenly as possible. A half, 2/3, 3/4, these are the dimensionalities of the regular polytopes, the most balanced ways to share a space. In between them, the arrangement sense are less efficient, so the model avoids lingering there. It's almost like the energy levels of an atom, only certain configurations are stable, and the system snaps to the nearest one. Out of a messy optimization falls clean, discrete structure. Put it all together and you get a whole spectrum of regimes, depending on how many features the model tries to fit per neuron. At one extreme, every neuron is monosemantic, one feature each, perfectly interpretable. Then 3 features in 2 neurons, 5 features in 3, 8 in 5, each a different geometric code, each a little more polysemantic than the last. The colors here run from monosemantic to polysemantic as the packing tightens. There is no single answer to how a network represents features. There's a continuum, and where a model lands on it is set by the sparsity and importance of the features it's trying to hold. Something equally surprising shows up when you watch the model train. The loss does not glide down a smooth slope. It drops in sudden steps with long flat stretches in between, like a staircase. Each of those cliffs is a moment of discovery, the instant the model reorganizes its features into a better arrangement, snapping, say, from leaving a feature out to slotting it into an antipodal pair. The authors compare these to energy levels. The model jumps from one stable configuration to the next. It's a tiny, clean echo of something we see in big models too, where new capabilities can appear abruptly, rather than gradually. These dynamics connect to one of the strangest phenomena in modern machine learning, double descent, where giving a model more data or more capacity can make it temporarily worse before it gets better again. In the toy model, the authors find their own version of this, and they can trace it directly to how features compete for room and rearrange their packing. That's a big deal, because it suggests superposition isn't some isolated curiosity. It's tangled up with how neural networks generalize in the first place, the very thing that makes them work. So far, we've only asked whether a network can store features in superposition, but there's a far deeper question. Can it compute on them, run an actual function, without first unpacking them into clean neurons? To test this, the author set the model a small task: take each input feature and output its absolute value, a genuinely nonlinear operation. If the model can do that while the features are still superimposed, it would mean superposition isn't just a storage trick, it's a computational medium. And it can. Look at this little learned circuit. Even with features packed together as antipodal pairs, the model computes absolute values by combining them through the ReLU. Carefully chosen positive and negative weights, plus the bias, create interference patterns that cancel out the unwanted parts and leave exactly the magnitude behind. The +1s and -1 here are the model arranging that cancellation. The lesson is profound. Real networks may be performing surprisingly sophisticated computation directly on top of superimposed features, never bothering to give each feature a clean, private neuron at all. Now the natural objection: this is a tiny, hand-built model, so why should we believe anything like it happens inside GPT-Scale systems? The answer is that the conditions that drive superposition here, many features, most of them sparse, some more important than others, and not nearly enough width to give each its own dimension, are exactly the conditions real networks operate under. The toy model isn't claiming to be a brain. It's isolating a force, and that force is almost certainly acting, quietly and everywhere, inside the large models we actually care about. And that is why this paper reshaped interpretability. If neurons are polysemantic because of superposition, then staring at a single neuron will rarely tell you a clean story. The real features are smeared across many neurons in directions that don't line up with any one of them. To understand the model, you first have to unmix the superposition, recover the original feature directions hiding in the tangle. That is precisely the goal of the sparse autoencoders that came later, tools built to pull monosemantic features back out of a polysemantic network. Toy models gave that whole research program its foundation. So step back and look at what this little model taught us. A neural network is best understood not as a tidy rack of one-concept neurons, but as a compressed communication channel, holding far more than its raw size suggests. Superposition explains the polysemantic neurons that frustrated us, the sudden jumps during training, the strange geometry of features, and, ultimately, why looking inside a network is so hard. But it also points the way forward. If we can understand the packing and learn to undo it, the black box finally starts to open. And remarkably, the whole story falls out of a model simple enough to fit on a single slide.